Scientists tell us the universe is about 13.8 billion years old. That number appears in textbooks, documentaries, and classrooms around the world. It's calculated using some of our most precise tools: measurements of ancient light, observations of distant galaxies, and the rate at which space itself is expanding. And yet, not everything fits. When astronomers look closely at the oldest stars, some of them seem too old, older than the universe should allow. Their chemical makeup suggests they formed extremely early, but their apparent age pushes uncomfortably close to the supposed beginning of time itself. Then there is the light. Some of the most distant galaxies appear brighter, more developed, and more structured than expected. According to our models, they shouldn't have had enough time to grow that way. It's as if the universe began building complexity faster than we thought possible. These aren't mistakes. They're not simple errors or bad measurements. They're quiet inconsistencies, small tensions in an otherwise elegant picture. The current explanation for the universe's age relies heavily on how fast it is expanding today. This value, called the Hubble constant, should be the same no matter how we measure it. But it isn't. When we calculate expansion using the early universe, we get one answer. When we measure it using nearby galaxies, we get another. Both methods are precise, both are trusted, and yet they disagree. This disagreement is known as the Hubble tension, and it hasn't gone away. Instead, it has grown sharper with better data. Some scientists wonder if dark energy, the mysterious force driving expansion, has changed over time. Others suggest that the early universe behaved differently than our equations assume, and a few quietly ask an even deeper question. What if the moment we call the beginning wasn't the true beginning at all? What if the universe didn't start with a single clean event, but emerged from something older, stranger, and harder to detect? These ideas are still speculative. Most researchers continue to accept the 13.8 billion year estimate. But science doesn't move forward by ignoring discomfort. It moves forward by sitting with it, by listening to the data, by allowing uncertainty to exist. And as you rest here now, letting your thoughts slow down, it's worth remembering this. The universe has never promised us simple answers. It reveals itself gradually, through faint light, through ancient stars, through questions that refuse to disappear. And as we continue, we'll drift deeper into those questions, not searching for conclusions, but exploring the quiet, expanding mystery that has been unfolding long before we were here, and will continue long after we fall asleep. As we drift deeper into the universe, the questions don't fade, they multiply quietly. For a long time, we believed every planet needed a star, a sun to orbit, a source of warmth, light, and direction. But the universe doesn't always follow expectations. Scattered throughout our galaxy are planets that belong to no star at all. They are known as rogue planets, worlds moving through space alone, unbound, silent, and dark. Some of them formed normally, circling young stars in busy solar systems, but gravity can be chaotic. A close encounter, a passing giant, a slow instability over millions of years, and suddenly a planet is flung outward, released into interstellar space. Others may have never had a star to begin with. They formed directly from collapsing clouds of gas, not massive enough to ignite fusion, but heavy enough to become planets, failed stars, or perhaps something entirely their own. Without a sun, these worlds are cold, their skies are black, no sunrise, no sunset, only faint starlight stretched thin across endless distance. And yet, they may be everywhere. Astronomers estimate there could be billions of rogue planets in the Milky Way alone, possibly more than the number of stars. Invisible unless they briefly pass in front of a distant light source, revealing themselves by the smallest bend or flicker. Each one is a quiet traveler, spinning slowly, carrying its own history through the dark. Some scientists wonder whether deep beneath their frozen surfaces, warmth could still exist. Heat left over from formation, radioactive decay, hidden oceans locked under miles of ice, sheltered from space, unchanged for billions of years. Life is unlikely, but uncertainty remains, because the universe often hides complexity in places we once dismissed as empty. These solitary planets remind us that not all stories revolve around stars. Not every world needs a center. Not every journey needs a destination. And as Earth moves through space right now, quietly orbiting its sun, our galaxy itself is drifting, carrying stars, gas, dust, and dark matter along enormous arcs shaped by gravity we cannot see. Nothing is truly still. Even now, as your body rests, space is moving through space. Planets without suns pass unseen. Light from distant galaxies continues its long travel, and the universe, vast and patient, allows worlds to exist in ways that feel almost impossible. And from here, without pause or urgency, we continue outward, towards stranger matter, deeper darkness, and forces that shape everything, even when they leave no light behind. As we move farther out, the universe begins to feel less like a place and more like a process. Most modern cosmology describes a universe that began with a single expansion and has been growing ever since. Space stretching, galaxies drifting apart, time moving forward without reversal. But not every theory agrees. Some physicists have wondered whether the universe might be cyclical, not born once, but many times. A cosmos that expands, slows, collapses, and then begins again. In these models, the universe doesn't end in silence or freeze forever into darkness. Instead, it reaches a turning point. Gravity pulls everything inward. Matter grows dense. Temperatures rise. And rather than collapsing into nothing, the universe rebounds, a cosmic reset. Each cycle would erase much of what came before. Galaxies would vanish, stars would be crushed, structure would dissolve. But not necessarily everything. Some theories suggest faint traces could survive, faint patterns in radiation, tiny irregularities in the fabric of space, hints that this universe may not be the first to exist. If that were true, then the moment we call the beginning wouldn't be a true beginning at all. It would be a transition, a doorway between cosmic eras. These ideas are speculative. They sit at the edge of what we can test, but they are taken seriously because they emerge from mathematics, not imagination. The universe has already surprised us before. We once believed space was static. It wasn't. We once believed time was absolute. It wasn't. We once believed nothing could escape a black hole. That may not be entirely true either. So when scientists ask whether the universe could recycle itself, they aren't guessing wildly. They're following questions to their quiet conclusions. If the universe has gone through many cycles, then time may stretch far beyond what we can observe. An ocean with no shore, each expansion just one wave among countless others. And in that view, existence becomes less fragile, not a single chance, not a one-time event, but part of a long, repeating rhythm. As you rest now, with thoughts slowing and attention drifting, this idea carries a strange comfort, that the universe is not rushing toward an end, that it has learned patience on scales beyond comprehension. Perhaps nothing is ever truly lost. Perhaps the universe doesn't forget, it transforms. And as we continue, we'll move closer to the oldest thing we can actually see. Not stars, not galaxies, but light itself, traveling since the universe first became clear enough to let it go. As the universe expanded and cooled, there came a moment when everything changed quietly. Before this moment, the universe was filled with heat and light, but light couldn't travel freely. Space was dense, opaque, and restless. Photons were constantly scattered, trapped in a glowing fog of charged particles. Then, about 380,000 years after the expansion began, the temperature dropped enough for atoms to form. Electrons settled into place, the fog cleared, and light was finally released. That light has been traveling ever since. We call it the cosmic microwave background, not because it's dramatic, but because it's subtle. A faint, uniform glow that fills the entire universe, arriving from every direction at once. It doesn't come from stars or galaxies. It comes from the universe itself, when it first became transparent. The photons we detect today began their journey long before Earth existed, long before the Milky Way formed. They have crossed expanding space for more than 13 billion years, stretched thinner and cooler along the way. What was once brilliant light is now microwaves, quiet, nearly invisible, but still present. They pass through your walls, through your body, through the space around you. This ancient light carries information, tiny variations in temperature, barely noticeable differences that map the early universe's structure. From these faint patterns, scientists can reconstruct what the universe looked like in its infancy, where matter was slightly denser, where gravity would eventually pull gas together, where stars and galaxies would later emerge. In a sense, this light is a photograph, not of objects, but of conditions, a snapshot of the universe before it had faces or shapes. And it's remarkably smooth. That smoothness tells us something profound. The early universe was balanced, nearly uniform. Any chaos came later. And yet, without those tiny imperfections, those slight unevennesses, nothing would exist. No stars, no planets, no life. The cosmic microwave background is both calm and decisive, a reminder that even the smallest variations can shape everything that follows. As you lie here now, letting thoughts blur and soften, this ancient light continues to arrive. Every moment, everywhere. It doesn't rush, it doesn't fade, it simply exists, carrying the memory of the universe's first clarity. And from that first light, we move forward towards stranger worlds, unusual matter, and places where physics begins to bend under its own weight. From the universe's first light, matter slowly gathered, gas cooled, gravity pulled, stars ignited. And around some of those stars, planets formed, not all of them familiar. In certain regions of the universe, chemistry takes a different path. If a planetary system forms with more carbon than oxygen, the rules change. Instead of silicate rock and water, carbon dominates. Under immense pressure, that carbon can crystallize. The result is something almost unreal. A planet where large portions of its interior may be made of diamond. At least one such world has been identified as a strong candidate. It orbits a pulsar, the dense, rapidly spinning remnant of a dead star. What remains is not a gentle sun, but a collapsed core emitting beams of radiation like a cosmic lighthouse. The planet itself is nothing like a gemstone you could hold. Its surface would be scorching, its environment hostile. But deep beneath, carbon lattices could stretch for thousands of miles. An entire world shaped by pressure and time. These strange planets remind us that nature doesn't aim for beauty. Beauty emerges as a side effect of physics. But the universe doesn't only build, it also collapses. When massive stars reach the end of their lives, gravity wins. The core implodes. Matter is crushed beyond ordinary limits. What remains is a neutron star, an object only about 20 kilometers wide, yet more massive than the Sun. Inside, atoms are destroyed. Electrons are forced into protons. Matter becomes a dense ocean of neutrons. The density is almost impossible to imagine. A single teaspoon would weigh billions of tons. Even a droplet smaller than a raindrop would outweigh Mount Everest. These objects spin rapidly, sometimes hundreds of times per second. They bend space around them. Some of the universe's strangest behavior doesn't come from matter at all, but from space itself. We often imagine light traveling in straight lines, moving cleanly from one place to another. But in reality, light follows the shape of space. And space, under the influence of gravity, can curve. When massive objects, like galaxy clusters, gather enormous amounts of matter, they don't just pull on stars and gas, they bend the geometry around them. As light from a distant galaxy passes through this warped region, its path bends, not because light is weak, but because space itself is no longer flat. This effect is called gravitational lensing. Sometimes the result is subtle. A galaxy appears slightly stretched. An image looks distorted, like it's being viewed through glass. Other times, the effect is dramatic. Astronomers have observed complete rings of light, perfect circles formed when a distant galaxy aligns precisely behind a massive foreground object. In rare cases, the same galaxy appears multiple times in the same image, its light arriving along different curved paths. Even more strange, these paths are not equal. Light taking a longer route arrives later, which means in certain situations, we don't just see multiple images of the same object, we see it at different moments in time. There have been instances where astronomers watched a distant star explode and then watched it explode again, not because it happened twice, but because gravity delayed one version of the light. Space in these moments becomes a storyteller, showing us how flexible reality can be. Gravitational lensing also reveals something invisible: dark matter. We cannot see it directly. It does not emit light. It does not reflect it or absorb it. But it has mass, and mass bends space. By studying how background light is distorted, scientists can map the presence of dark matter, finding vast halos surrounding galaxies, extending far beyond anything we can see. These halos hold galaxies together. Without them, stars would drift away, structure would fall apart. And yet, dark matter remains a mystery. As you rest now, it's worth realizing that gravity is shaping more than orbits and motion. It's shaping perception itself. What we see in the universe is not always what is happening now, not always what happened once. Sometimes it is a carefully delayed message, folded by space, delivered across billions of years. Light doesn't simply travel, it navigates. And gravity, patient and silent, guides it, curving the universe into forms that reveal truths we could never see directly. From here, the universe continues inward, toward the first stars, the ones that burned brightest, lived shortest, and changed everything. Before galaxies had shape, before planets had names, the universe was dark. Not empty, not silent, just waiting. After the first light faded into the background, gravity continued its slow work. Hydrogen and helium gathered in faint clouds, drawn together by the slightest imperfections left in the early universe. Eventually, those clouds collapsed, and the first stars were born. They were nothing like the stars we see today. There were no heavy elements, no carbon, no oxygen, only the simplest atoms pressed together by gravity. Because of this, the first stars grew enormous. Some may have been hundreds of times more massive than the Sun. Their cores burned at extreme temperatures, forcing nuclear reactions to race forward. These stars lived fast. They shone intensely, possibly 1,000,000 times brighter than our Sun, and they died young. In just a few million years, their fuel was exhausted. Gravity reclaimed them. Some collapsed directly into black holes. Others exploded with unimaginable force. Those explosions mattered. Inside those brief, violent deaths, the first heavy elements were created: carbon, oxygen, iron, the materials that would one day form planets, oceans, and living cells. In that sense, every atom heavier than hydrogen carries the memory of a star that no longer exists. None of these first stars survive today. Their lives were too short. Their light has long faded, but their influence is everywhere. They transformed the universe from a simple place into a complex one. They heated surrounding gas. They reshaped early galaxies. They ended the long cosmic night. And as the universe slowly filled with structure, something new began to emerge. Not light from stars, but unseen matter guiding where stars would form next. Dark matter. It does not glow. It does not interact with light. Yet it outweighs normal matter by a wide margin. As galaxies formed, dark matter created invisible scaffolding, vast filaments stretching across space, guiding gas into knots where stars could ignite. Without it, the universe would look very different. Galaxies would be fragile, structure would unravel. And even now, as you rest, dark matter is moving. It flows through your body, through the earth, through the space around you. Trillions of particles pass through you every second, leaving no trace, silent, unnoticed. The universe does not need to announce itself. It builds quietly, it shapes gently, it remembers in ways we are only beginning to understand. And from these first stars, we move onward, toward galaxies that glow without stars, toward missing matter, and toward mysteries that grow deeper the more we observe. As the universe matured, galaxies became the great cities of space. Billions of stars bound together by gravity, glowing across unimaginable distances. But not all galaxies follow the rules. In recent years, astronomers have found galaxies that shine faintly or almost not at all. Some contain vast amounts of gas and dark matter, yet form very few stars. Others appear to have lost most of their stars entirely. These are sometimes called ghost galaxies. They drift through space as pale smudges, barely visible even to powerful telescopes. Their mass suggests they should be full of stars, but the light is missing. One possibility is violence. Galaxies live in crowded neighborhoods. Close encounters can rip stars away, scattering them into intergalactic space. Over time, a once bright galaxy can be stripped down to a shadow of itself. Another possibility is failure. Some galaxies may never have formed many stars at all. Their gas could be too diffuse, their internal motion too chaotic. Without the right balance, star formation simply never begins. And then there are even stranger cases. A few galaxies appear to contain almost no dark matter. This is deeply unsettling. Dark matter is thought to be the framework that allows galaxies to exist. Without it, stars should fly apart, yet these galaxies remain intact. How they formed is still unknown. They may be rare accidents, the result of precise cosmic collisions that separated normal matter from dark matter. Or they may be signs that our understanding of gravity is incomplete. None of these explanations fully satisfy. What's clear is that the universe is not uniform in its behavior. It allows exceptions, outliers, quiet contradictions. And those contradictions matter. They force us to test our assumptions, to question what we believe we understand. As you rest now, with thoughts drifting freely, imagine these faint galaxies moving silently through the dark, holding secrets that resist explanation. They remind us that light is not guaranteed, that structure does not always bloom, that sometimes the universe builds something and then withholds the reason. Beyond these ghostly systems lies an even larger pattern, one that connects all galaxies, bright or dim, into a vast, unseen structure, a cosmic web. Threads of matter stretching across billions of light years, linking clusters of galaxies like nodes in an immense network. And when we step back far enough to see that structure, it begins to resemble something strangely familiar. When astronomers began mapping the universe on its largest scales, they expected randomness. Galaxies scattered like grains of sand, clusters appearing by chance. But that isn't what they found. Instead, a pattern emerged. Galaxies gather along vast filaments, long thread-like structures stretching across hundreds of millions of light years. Between them lie enormous voids,
regions almost completely empty. Together, these filaments and voids form what is known as the cosmic web. It is the largest structure ever observed. And when scientists stepped back far enough to see it as a whole, something unsettling appeared. The pattern looked familiar. The cosmic web bears a striking resemblance to a neural network, the branching structure of neurons in the human brain. Dense nodes connected by long filaments. Information pathways mirrored in matter and gravity. Of course, the universe is not thinking. The similarity is visual, not conscious. The physics that shape galaxies and the biology that shape brains are entirely different. And yet, the resemblance remains. It's a reminder that complexity often emerges from simple rules. Gravity pulling matter together, energy flowing along the easiest paths, structures growing where conditions allow. In the brain, electrical signals follow networks shaped by evolution. In the universe, galaxies follow networks shaped by gravity and dark matter. Different scales, different laws, strangely similar outcomes. Dark matter plays a crucial role here. It forms the invisible scaffolding of the cosmic web. Normal matter, gas, dust, stars, flows along these filaments, collecting where dark matter is densest. Without dark matter, the web would collapse. Galaxies would form too slowly. The universe would remain thin and scattered. And yet, dark matter itself remains unseen. We know it by its influence, not by its appearance, by how it bends light, by how it shapes motion. As you rest now, it's worth realizing that you exist inside this structure. Your galaxy is a single glowing knot in an immense network. Your planet an almost invisible point within that knot. And still, the same physical laws apply everywhere. The same gravity that shapes galaxies shapes your body. The same atoms formed in ancient stars form your thoughts. The universe is not divided into separate layers of importance. Small and large are connected. And within this vast web, time itself continues to move in subtle, uneven ways, not flowing the same everywhere, not ticking at a single universal pace. As we continue, we'll move toward one of the quietest but strangest ideas in physics, that time can stretch, slow, and bend depending on where you are in the universe.
We often think of time as steady, a quiet, universal rhythm that moves forward at the same pace for everyone, everywhere. But time is not that simple. According to relativity, time is woven into the fabric of space itself. It stretches, it slows, it responds to gravity and motion. Near massive objects, time moves more slowly. Close to a black hole, seconds can stretch into hours when compared to distant space. This isn't speculation. It's been measured. Satellites orbiting Earth experience time differently than clocks on the ground, and corrections are required for GPS systems to function accurately. Time is flexible. But some scientists wonder if this flexibility extends even further. Could time flow at slightly different rates across vast regions of the universe? Could the early universe have experienced time differently than we do now? These questions arise from observations that don't quite align. Subtle differences in cosmic expansion, large-scale structures that seem to grow faster than expected, patterns that hint the universe may not be as uniform as once believed. If time varied in the early cosmos even slightly, it could change how we interpret everything. A universe that appears older in one region might be younger in another. Events we think happened simultaneously might not have. This idea is controversial. It challenges deeply held assumptions, but it is not dismissed, because physics has already taught us that intuition is unreliable on cosmic scales. Time slows mere gravity. Time stretches with speed. Time bends with space. So why should it be identical everywhere? As you rest now, allowing awareness to soften, it's worth remembering that your experience of time is shaped by where you are, by Earth's gravity, by your motion through space, by the quiet pull of mass around you. Even sleep changes time. Moments stretch, thoughts blur, the clock loses its grip. The universe experiences something similar, but on scales we can barely imagine. Some regions evolve faster, others linger. And as galaxies drift apart and stars age, time continues its uneven flow, quietly shaping every process, every transformation. Ahead of us lies something vast and invisible, surrounding our galaxy like a shadow, a hidden halo of the Milky Way. When we picture the Milky Way, we imagine a glowing spiral, a bright disk filled with stars, dust, and clouds of gas. But that familiar image is only the center. Surrounding the visible galaxy is something far larger and mostly unseen. A vast halo extending far beyond the spiral arms, wrapping the Milky Way in a quiet sphere. This halo is made of two things: diffuse gas, thin, hot, and spread over enormous distances, and dark matter, dense, invisible, and dominant. The dark matter halo is massive. It outweighs all the stars in the galaxy combined. Without it, the Milky Way would not hold together. Stars in the outer regions would drift away into intergalactic space. We know this halo exists because of how stars move. They orbit too fast for the visible matter alone to keep them bound. Something unseen is holding them in place. The halo extends hundreds of thousands of light years from the galaxy's center, far beyond where stars are common, far beyond what our eyes can detect. Within it are ancient star clusters, globular clusters, dense collections of old stars that orbit like relics from the galaxy's early history. Some stars in the halo are older than the Milky Way's current shape. They formed in smaller galaxies that later merged into ours. Their paths still carry the memory of those long-lost systems. The halo is not smooth. It is laced with streams, long trails of stars torn from smaller galaxies as they were absorbed, ghostly evidence of past collisions. The Milky Way is not a static object. It is a survivor of countless mergers shaped by gravity and time. And beyond the halo, the galaxy continues to interact with its surroundings, drawing in gas, influencing nearby dwarf galaxies, slowly preparing for a future collision with Andromeda. All of this is happening quietly, on timescales far beyond human awareness. As you rest now, Earth continues its orbit. The Sun moves around the galactic center. The Milky Way drifts through the cosmic web, and the halo moves with it, an invisible companion, shaping motion, holding structure together. Ahead lies a glimpse even deeper into the past, light that has traveled nearly the entire age of the universe to reach us, a view of galaxies as they were only a few 100 million years after everything began. When we look deep into space, we are also looking back in time. Light does not arrive instantly. It moves at a finite speed, crossing expanding space year by year. So the farther away an object is, the older the image we see. For most of human history, our view stopped relatively close to home, nearby stars, neighboring galaxies, the recent universe. But with more powerful telescopes, that boundary has moved. Today, astronomers have detected light from galaxies that formed just a few 100 million years after the universe began. These galaxies are small, faint, and fragile, nothing like the grand spirals we see nearby. Yet they exist far earlier than we once thought possible. According to older models, the universe at that time should have been too young, too chaotic, too short on heavy elements to build structure so quickly. And yet, the light is there. It has been traveling for more than 13 billion years, passing through empty space, sliding past forming galaxies, being stretched by cosmic expansion until its wavelength shifted into infrared. When that light finally reaches us, it is faint, but it carries information. It tells us that stars were forming early, that galaxies assembled faster than expected, that the universe did not wait patiently before beginning to organize itself. This raises quiet questions. Did gravity work differently in the early universe? Was dark matter more efficient at gathering matter? Or did the first stars ignite sooner than our models predict? No single answer explains everything. What we know is this: the early universe was not as simple as we imagined. It was active, creative, eager to build. As you rest now, letting your thoughts soften, imagine that ancient light, leaving its source before Earth existed, before the sun ignited, before the Milky Way settled into its familiar shape. That light crossed a universe that was changing even as it traveled, galaxies forming behind it, stars being born and dying along its path. By the time it reaches your eyes, it carries a message from a world long gone, a universe still learning how to be itself. And as we receive those messages, new questions arise. If structure formed so early, what else might exist beyond our current horizon? What events happened that we will never see because their light will never reach us? The universe is vast, but not all of it is observable. Some regions are forever beyond our view. And yet, even within what we can see, patterns emerge, patterns that repeat across scales, linking galaxies, clusters, and voids into something strangely familiar. From here, we drift outward again, toward the architecture of the universe itself and the shapes it prefers to build. As our understanding of the early universe deepens, one quiet anomaly continues to resist explanation. It appears in the oldest light we can observe, the cosmic microwave background, the faint afterglow of the universe's first clear moment. When scientists mapped this ancient light in detail, they expected randomness, tiny temperature variations scattered evenly across the sky, small differences, but nothing dramatic. Most of the map fits that expectation, except for one place. There is a region of sky that is noticeably colder than the rest, not by much, just a fraction of a degree, but on cosmic scales, it is enormous. It spans an area far larger than our local group of galaxies. This region is known simply as the cold spot. At first, it seemed like a statistical fluke, a rare but possible irregularity. But as measurements improved, the cold spot remained. Its size and depth don't sit comfortably within standard models of the early universe. The odds of such a feature appearing by chance are small, though not impossible. One explanation is that the cold spot lies behind a massive cosmic void, a region with very little matter. As light passes through this emptiness, it can lose a small amount of energy, arriving cooler than expected. This idea explains part of the anomaly, but not all of it. Another possibility is far stranger. Some physicists have suggested that the cold spot could be the imprint of a collision, not between galaxies, but between universes. In certain models of inflation, our universe may be just one bubble among many. If two such bubbles brushed against each other in the earliest moments, the interaction could leave a scar, a subtle temperature difference, a faint memory written into the oldest light. There is no proof of this, and extraordinary claims require extraordinary evidence. But the fact that such ideas are even discussed speaks to how deeply the cold spot challenges our assumptions. The universe usually hides its secrets behind complexity. This one hides in plain sight. As you rest now, letting awareness drift, imagine that patch of sky, quietly cooler, quietly different, carrying a question we haven't yet learned how to answer. It does not announce itself. It does not demand attention. It simply exists. And sometimes in science, that is enough to unsettle everything we think we know. From here, we move closer to home, to a relationship shaped by gravity and time, one that has been slowly changing since long before life appeared on Earth, the bond between our planet and its silent companion, the Moon.
The Moon has been a constant presence in our sky for as long as humans have looked up. A steady rhythm, a familiar glow. But the Moon is not as still as it appears. Every year, it drifts a little farther away from Earth, about 3.5 centimeters, roughly the rate at which fingernails grow. This slow retreat has been happening for billions of years. When the Moon first formed, it was much closer. So close that tides were stronger, days were shorter, and Earth spun much faster than it does now. The reason lies in a quiet exchange of energy. As the Moon's gravity pulls on Earth's oceans, it creates tidal bulges. Earth rotates beneath these bulges, dragging them slightly ahead of the Moon's orbit. This offset transfers energy outward, pushing the Moon into a higher orbit while gradually slowing Earth's rotation. The process is invisible in daily life, but over immense spans of time, its effects are profound. Days lengthen, the Moon recedes, the relationship changes. In the distant future, if nothing disrupts the system, Earth and the Moon may become tidally locked. The same side of Earth would always face the Moon, just as the same side of the Moon faces Earth today. No sudden ending, no catastrophe, just a slow settling into balance. The Moon also carries a record of deep time. Its surface is scarred by impacts, preserved almost perfectly. Without atmosphere or plate tectonics, nothing erases the past. Each crater is a memory.
each shadowed basin a timeline. By studying the moon, scientists learn not only about its history, but about Earth's early years as well, a time when impacts were common and the inner solar system was still taking shape. As you rest now, it's easy to forget that even familiar things are changing. The moon feels permanent, unmoving, but the universe rarely allows true stillness. Even now, the moon is inching away. Earth is spinning more slowly. Time is stretching itself thin. And beyond this gentle dance lies a far more intimate one. Stars so close that they share matter, exchange mass, and alter each other's fate. Two stars bound together, quietly reshaping themselves through gravity alone.
Some stars live alone, drifting quietly through space. Others are born in pairs. Binary star systems are common in the universe. Two stars bound by gravity, orbiting a shared center of mass. From a distance, they may look peaceful, but when stars orbit too closely, their relationship becomes intimate. As stars age, they change, they swell, their outer layers expand. In a close binary system, one star can grow so large that its atmosphere begins to spill toward its companion. Gravity pulls gas across the gap, creating a slow, spiraling stream of matter. This exchange can be gentle, lasting millions of years, or violent, triggering sudden bursts of light as matter crashes onto the receiving star. The donor star loses mass, the receiver grows hotter and faster spinning. Both are changed. Sometimes the process strips a star down to its core, leaving behind a compact, glowing remnant. In other cases, the stars merge entirely, becoming a single, more massive object. These interactions shape some of the most extreme objects in the universe. Certain types of supernovae begin this way, when a white dwarf star steals too much matter and collapses in a catastrophic explosion. Neutron star pairs, black hole binaries, and gravitational wave sources often trace their origins to these quiet exchanges. From the outside, nothing dramatic may be visible, but inside the system, gravity is rewriting the future. As you rest now, letting thoughts soften, imagine two stars moving in a slow cosmic dance, close enough to touch, close enough to change each other forever. There is something oddly human in this process. Two bodies influencing one another simply by being near, sharing energy, sharing material, sharing fate. But the universe does not attach meaning. It follows rules. And one of those rules is that even emptiness is not truly empty. Beyond stars and planets lies a space that appears silent, a vacuum. Yet even there, activity never stops. Particles flicker into existence and vanish. Energy hums quietly beneath the surface of nothingness. From this restless background arises one of the most mysterious forces we know, the energy driving the universe's accelerated expansion, dark energy. It fills space, it pushes galaxies apart, and it reminds us that what seems empty may be the most powerful thing of all. When we imagine empty space, we picture nothing, a perfect vacuum, still, dark, and quiet.
But the universe does not allow true emptiness. Even in the deepest regions between galaxies, far from stars, dust, or gas, space is alive with subtle activity. According to quantum physics, what we call nothing is a restless field. Tiny particle-antiparticle pairs constantly appear and vanish. They exist for only the briefest moments, borrowing energy from the vacuum before returning it. This happens everywhere, all the time. These fluctuations are not just mathematical ideas, they have measurable effects. They influence how particles behave. They affect the forces that shape reality at the smallest scales. And on the largest scales, they may do something even more remarkable. They may help explain why the universe is expanding faster and faster. Observations show that galaxies are not merely drifting apart, their separation is accelerating. Something is pushing space itself to stretch more rapidly over time. We call this influence dark energy. We don't know what it is. We don't know where it comes from. We only know its effect. It dominates the universe. Normal matter, stars, planets, gas, makes up only a small fraction of everything that exists. Dark matter outweighs it several times over, and dark energy outweighs both combined. It fills space evenly. It does not clump. It does not form structures. It simply pushes. As space expands, more dark energy appears, not because it's created, but because there is more space to contain it. This creates a feedback loop. Expansion leads to more dark energy. More dark energy leads to faster expansion. Over immense spans of time, this process reshapes the cosmos. Galaxies move beyond each other's reach. Light from distant regions will never arrive. The observable universe slowly becomes smaller, not because it shrinks, but because more of it slips away. And yet this expansion is not violent. It is smooth, gentle, almost tender. As you rest now, it may feel strange to think that space itself is active, stretching beneath everything, quietly influencing the fate of all structure. The silence around you is not absence, it is fullness beyond perception. And within that fullness, time continues its uneven flow. Matter continues its slow transformation, and the universe continues to change, not with urgency, but with patience learned over billions of years. From here, we turn inward again, towards the oldest survivors in the cosmos, stars that formed before galaxies fully took shape and still carry the chemistry of a younger universe.
Galaxies feel ancient. Vast collections of stars that seem as old as the universe itself. But some stars are older than the galaxies they now call home. Galaxies are not born fully formed. They grow over time, merging, absorbing smaller systems, drawing in gas, and reshaping themselves through gravity. In this process, stars can be captured. Long ago, small proto-galaxies formed their own stars. Some of these early systems later collided with larger galaxies. Their structures were torn apart, but many of their stars survived. Those survivors still orbit today. They are found in the outskirts of galaxies, or in tightly bound globular clusters, dense spheres of ancient stars moving as a group through space. Some of these stars are more than 13 billion years old. They formed when the universe was still young, when heavy elements were rare and conditions were simple. Their chemistry reflects that.
They contain very little metal, mostly hydrogen and helium, with traces of heavier elements created by the first generations of stars. By studying these ancient stars, scientists can reconstruct the universe's early history. They are time capsules, unchanged for billions of years. Their light is faint, their motion slow, but their information is priceless. As you rest now, imagine a star that has been shining since near the beginning of everything. It has witnessed the formation of galaxies, the birth and death of countless stars, the slow assembly of structure across the cosmos. And yet it continues, quietly burning, following the same physical laws it always has. These ancient stars remind us that survival in the universe does not require brilliance. It requires stability. While stars evolve and die, some persist long enough to outlast entire galactic structures. And still, even with all this age and endurance, mysteries remain. Because there are galaxies that seem to lack something essential. Systems where stars exist without the invisible glue thought to hold everything together. Galaxies without dark matter. They challenge our understanding of gravity, of formation, of the universe's underlying rules. From here, we move toward these quiet contradictions, places where expectations fail, and where the universe gently suggests that it may still be hiding something fundamental.
Dark matter is often described as the skeleton of the universe, the unseen framework that gives galaxies their shape and keeps stars from drifting apart. That's why a certain discovery felt so unsettling. Astronomers identified a small number of galaxies that appear to contain little or no dark matter at all. At first, the idea seemed impossible. Without dark matter, galaxies should be fragile. Their stars should escape, leaving nothing behind. And yet, these galaxies remain intact. They are faint, diffuse, barely visible even with powerful telescopes. Measurements suggest that almost all of their mass can be explained by ordinary matter alone. This contradicts decades of observation. One explanation is that these galaxies are cosmic accidents. Perhaps they formed during violent interactions, where dark matter was stripped away while stars remained bound. Such collisions would need to be precisely tuned, rare but not impossible. Another idea is more radical. Maybe gravity behaves differently in certain environments. If so, dark matter might not be required everywhere. The laws we apply universally may have limits we haven't yet discovered. Neither explanation is fully satisfying. The galaxies are too stable, too consistent, too real to ignore. They sit quietly in the universe, not making noise, not demanding attention, simply existing as exceptions. As you rest now, it's worth remembering that science advances not only through confirmation, but through discomfort, through observations that refuse to fit neatly into theory. These galaxies are reminders that the universe is under no obligation to match our expectations. It reveals itself slowly, sometimes reluctantly. And just beyond these puzzles lies something even closer to home. Something passing through you right now, unnoticed, unchanged. Dark matter itself. As Earth moves through the Milky Way, it passes through a vast halo of dark matter. Trillions of dark matter particles stream through every square centimeter of your body each second. They do not collide with your atoms. They do not leave marks. They do not interact in any way we can detect directly. They are simply there, silent, ever-present, essential. Without dark matter, galaxies would not form. The cosmic web would unravel. Structure would fail to emerge. And yet, we still don't know what dark matter is made of. It passes through you as you rest, through your walls, through the earth itself. A quiet reminder that the universe is not only around you, it is moving through you. And from here, we turn back to the night sky, to stars that hum silently, vibrating with information hidden beneath their glowing surfaces.
Space appears silent. There is no air to carry sound, no medium for waves to travel the way they do on Earth. And yet, stars are not silent. Deep inside every star, pressure waves move through hot gas and plasma. They rise and fall, bounce and reflect, creating slow, rhythmic vibrations. These motions never reach our ears, but they leave signatures we can detect. Stars, in a way, sing. The study of these vibrations is called astroseismology, the science of listening to stars. By observing tiny changes in a star's brightness or surface motion, scientists can infer what is happening deep within. Each star has its own pattern. Its mass, age, size, and internal structure determine its rhythm. No two stars vibrate in exactly the same way. These vibrations reveal hidden layers. They tell us how fast a star rotates beneath its surface, how energy moves through its core, how close it may be to the end of its life. Some stars pulse gently, like a slow breath. Others beat more irregularly, responding to internal instability. Even our sun vibrates, expanding and contracting by small amounts every few minutes. By listening to these subtle changes, scientists have learned things that would otherwise remain invisible. They've measured stellar ages with surprising precision. They've confirmed theories about how stars evolve. They've discovered stars that look calm on the surface, but churn violently inside. As you rest now, letting thoughts soften, imagine a star far away, glowing steadily, appearing constant, yet filled with motion beneath its surface, a quiet orchestra of pressure and heat. This hidden activity reminds us that stillness in the universe is often an illusion. What looks calm may be dynamic. What looks simple may be complex. And stars are not the only objects that carry such hidden behavior. Beyond them lie relics even stranger, objects so dense that matter itself is crushed beyond familiar states, where gravity overwhelms everything else, places where a single drop of material could outweigh mountains. Neutron stars. They are small, dark, incredibly dense. Born from stellar collapse, they spin rapidly and bend space around them. They challenge intuition and stretch physics to its limits. And as we continue, we'll move toward these extreme remnants to understand how the universe behaves when matter can no longer resist gravity, and what remains when stars finally fall silent. When a massive star reaches the end of its life, there is no quiet fading. Its core collapses under its own gravity, falling inward faster than anything can escape. What remains is a neutron star. These objects are among the densest things in the universe, only about 20 kilometers across, yet containing more mass than the sun. Gravity here is so intense that ordinary matter cannot survive in familiar form. Inside a neutron star, atoms are crushed. Electrons are forced into protons, forming neutrons. Matter becomes a dense, exotic state, something closer to a single giant atomic nucleus than anything we encounter on Earth. The density is almost impossible to picture. A teaspoon of neutron star material would weigh billions of tons. Even a droplet smaller than a raindrop would outweigh the tallest mountains on our planet. These stars spin rapidly. Some rotate hundreds of times per second. Their magnetic fields are immense, trillions of times stronger than Earth's. As they spin, beams of radiation sweep through space. If one of those beams crosses Earth, we see a pulse, a lighthouse signal flashing with perfect regularity. These are pulsars. They are so precise that they rival atomic clocks. Their timing is so stable that tiny disturbances, a passing gravitational wave, a nearby object's pull, can be detected by changes in their rhythm. Neutron stars push physics to its limits. They test our understanding of matter, gravity, and space itself. Some may even contain more exotic states, superfluids, superconductors, or forms of matter we have not yet named. And yet they exist quietly, small, dark, often invisible unless their beams happen to point our way. As you rest now, it's worth reflecting on this contrast. The universe can compress the mass of a star into a space the size of a city. It can bend time, distort space, and create objects that defy intuition. And still, it does so without noise. Gravity does not announce itself. It simply acts. From neutron stars, the universe moves further, toward places where gravity wins completely, where even light cannot escape, and where our understanding begins to blur. Black holes. They are not cosmic vacuums, not destroyers of everything. They are something subtler, something stranger. And as we continue, we'll drift closer to these silent centers to explore what happens when matter, time, and space reach their final limits.
Black holes are often misunderstood. They are imagined as violent cosmic monsters pulling everything toward them. But in reality, black holes are quiet. They form when gravity overwhelms all other forces, when a massive star collapses so completely that no known pressure can stop it. What remains is not an object in the usual sense, but a region of space where gravity becomes absolute. At the boundary of a black hole lies the event horizon. This is not a physical surface. It is a point of no return. Cross it, and escape becomes impossible. Not even light can travel fast enough to leave. From a distance, a black hole looks calm. Stars can orbit it peacefully. Gas can swirl around it for millions of years before falling in. But closer to the center, the rules change. Time slows dramatically near the event horizon. To an outside observer, an object falling toward a black hole appears to freeze, fading slowly as its light is stretched and reddened. To the falling object, however, time feels normal until gravity tears matter apart. Inside the horizon, our equations stop making sense. Space and time trade roles. All paths lead inward. At the core lies what we call a singularity,
a point where density becomes infinite and known physics breaks down. Whether this singularity truly exists or whether new physics replaces it remains unknown. Black holes also shape the universe. Supermassive black holes sit at the centers of most galaxies, including our own. They influence star formation, regulate the flow of gas, and help shape galactic evolution. Despite their name, black holes are not empty. They are among the massive objects known. And they are not eternal. According to theory, black holes slowly lose mass over immense timescales through a process called Hawking radiation. They fade incredibly slowly, releasing energy until they disappear. Even the darkest objects in the universe may not last forever. As you rest now, imagine a place where time stretches towards stillness, where motion leads only inward, where the universe tests its limits of its own laws. Black holes are not endings, they are questions. And from these questions, we turn outward again, back to light, to galaxies, and to paths that bend and return in ways that defy straight lines.
We often imagine space as flat, a vast, open stage where objects move in straight lines forever. But space is not that simple. According to general relativity, space has shape. It can stretch, it can curve, and in some possibilities, it can wrap back on itself. This means the universe may not have an edge, not a wall, not a boundary where things stop. Instead, it may be finite but unbounded, like the surface of a sphere. On Earth, you can travel in a straight line without ever reaching an edge. Eventually, you return to where you started, not because you turned around, but because the surface itself curves. Some models suggest the universe could work the same way, but in 3 dimensions instead of 2. If that were true, a beam of light traveling in one direction long enough could, in theory, return to its origin. Not quickly, not noticeably, but eventually. This doesn't mean we would see copies of ourselves or familiar galaxies looping endlessly. The universe is expanding, light is stretched, time intervenes. But it does mean the concept of outside the universe may not make sense at all. There may be no edge to reach, only distance, only time. Observations so far suggest the universe is very close to flat. If it is curved, the curvature is subtle, far beyond what we can directly measure with current technology. Still, the possibility remains, and it changes how we think about existence. If the universe has no edge, then exploration has no final destination. There is no ultimate horizon to arrive at, only more space, more time, more quiet unfolding. As you rest now, this idea carries a gentle calm, that there is no boundary waiting to be crossed, no sudden ending written into the structure of reality. The universe may be vast, not because it stretches endlessly outward, but because it bends gracefully into itself. And within that curved space, stars are born, galaxies drift, and light takes paths shaped by gravity and time. Some of that light follows long, winding routes. It bends around massive objects. It splits, delays, and recombines. In rare cases, the same light can reach us more than once, arriving from different directions at different times. The universe, it turns out, is not always direct. It prefers elegant detours.
And as we continue, we'll follow those bending paths to see how gravity turns space into a lens and how distant events can appear more than once in our sky, quietly reminding us that even straight lines are shaped by where they travel.
Sometimes the universe tells the same story twice. Light usually takes the shortest path available, but when gravity bends space, the shortest path is no longer straight. Massive galaxy clusters can curve space so strongly that light from a single distant object is split and redirected along multiple routes. Each path is different. Some are longer. Some pass closer to dense regions where time itself slows slightly. The result is something quietly astonishing. The same event can reach us more than once. Astronomers have observed distant galaxies appearing as arcs, smudges, and near-perfect rings. These shapes are not illusions. They are the same object, seen along different gravitational paths. In rare cases, this effect becomes even striking. A star explodes in a distant galaxy, a supernova. Its light begins its journey across the universe. Some of that light takes a shorter route. Some takes a longer one, delayed by curved space and slowed time. Months or even years later, the explosion appears again. Not because it happened twice, but because the universe delivered the same moment on a different schedule. Time in these cases is not a single stream, it is braided. Gravitational lensing allows astronomers to study the universe in ways that would otherwise be impossible. It magnifies faint galaxies. It reveals dark matter by tracing how light bends around it. It turns gravity into a natural telescope. But it also carries a philosophical weight. It reminds us that what we see is shaped by where we stand, by the path information takes to reach us, by the invisible structure of space itself. As you rest now, consider this gently. Somewhere in the universe, light is still traveling toward us from events long finished, moments that no longer exist at their source, yet continue their journey through curved space. We are not seeing the universe as it is. We are seeing it as it was, filtered by gravity, stretched by expansion, delayed by distance. And in that delay, the universe gains depth. Past and present overlap. Single moments echo. History arrives out of order. From here, we move toward a quieter realization that not everything in the universe is meant to be seen. Some regions will forever remain beyond our reach. Some light will never arrive. And yet, within those limits, the universe continues to offer just enough. Enough mystery, enough beauty, enough unanswered questions to keep the journey going. The universe is vast, but it is not entirely accessible. There are regions so distant that their light will never arrive here, no matter how long we wait. This is not because those regions are hidden, but because space itself is expanding. As the universe grows, distant galaxies are carried away faster and faster. Beyond a certain distance, the expansion outpaces the speed of light. Light emitted from those regions can never close the gap. This boundary is called the cosmic horizon. It is not a wall. It is not an edge. It is simply the limit of what can influence us. Beyond it, galaxies still exist,
Stars still form. Time still flows. But their stories will never reach Earth. The observable universe is only a portion of what exists. A bubble of visibility shaped by time, speed, and expansion. And that bubble is shrinking in a subtle way. As dark energy accelerates expansion, more regions slip beyond our horizon. Galaxies that are visible today will eventually fade from view, their light stretched thinner and redder until it disappears entirely. In the far future, distant galaxies will vanish from the night sky. The universe will appear emptier, not because it is, but because its light can no longer reach us. As you rest now, this idea carries a quiet melancholy, that there are places we will never see, events we will never witness, questions that will never be answered by observation alone. And yet, there is also peace in this limit. The universe does not overwhelm us with everything at once. It reveals itself gradually within boundaries we can explore. Even within those boundaries, mysteries remain. Some galaxies glow brightly with stars, others barely shine at all. Some are rich with matter, others seem almost empty. And in the spaces between, vast voids stretch for hundreds of millions of light years, regions where almost nothing resides. These voids are not mistakes, they are part of the universe's architecture. Matter gathers into filaments and nodes, leaving behind enormous empty regions. The universe is not evenly filled, it is textured. And within this texture, gravity quietly shapes destiny. From here, we drift toward the largest empty places of all, cosmic voids, and what their silence may tell us about the universe's structure, its balance, and its hidden symmetry. Between the bright threads of the cosmic web lie places of deep stillness. Cosmic voids are enormous regions of space with very little matter, few galaxies, few stars, mostly emptiness. Some voids span hundreds of millions of light years. They are among the largest structures in the universe. At first glance, they seem unimportant, just gaps left behind as matter gathered elsewhere. But voids are not nothing. They shape how galaxies move. They influence the expansion of space locally. They help define the overall geometry of the universe. In many ways, voids are as important as the structures that surround them. Galaxies on the edges of voids tend to move outward, pushed gently by the lack of gravitational pull inside. Over time, matter drains away from these regions, making them emptier still. This creates a quiet contrast. Dense filaments grow denser, voids grow emptier. The universe becomes more structured, not less. Some scientists study voids to test fundamental physics. Because voids contain so little matter, they are clean environments, places where gravity and expansion can be observed with fewer complications. If gravity behaves differently on large scales, voids may reveal it. If dark energy changes over time, voids may respond first. In that sense, emptiness becomes a laboratory. As you rest now, imagine drifting through one of these vast regions. No stars nearby, no galaxies overhead, just darkness and distance. And yet, even here, space is not truly empty. Dark matter still passes through. Quantum fields still fluctuate. Dark energy still stretches space outward. The universe does not turn off its processes just because matter is scarce. There is a quiet beauty in this balance, structure and emptiness working together, neither dominating completely. Voids remind us that absence is part of design, that silence has shape, that nothingness can influence everything around it. And as the universe continues to expand, voids will grow larger, filaments will stretch thinner, galaxies will drift farther apart. Over immense spans of time, the cosmos will become darker and quieter. But even then, it will not be finished, because change does not require noise, it requires only time. From these quiet regions, we turn inward once more, toward our place in this vast structure, toward the question of scale, and toward the strange realization that the universe's largest patterns echo in the smallest places. As we move from the largest empty spaces back toward ourselves, something curious appears. Patterns repeat. The same structures that shape the universe on its grandest scales, networks, flows, balance between density and emptiness, also appear in places unimaginably small. Atoms form systems. Electrons orbit nuclei in probabilistic clouds. Energy moves along preferred paths. Zoom out, and galaxies do the same. This is not because the universe is copying itself, but because simple rules applied over and over often create familiar shapes. Gravity pulls matter together. Energy spreads outward. Systems settle into balance or drift toward instability. These rules apply everywhere. Inside your body, atoms formed in ancient stars follow the same physics as gas clouds forming new ones. There is no special exemption for scale. As you rest now, it may feel grounding to realize that you are not separate from this structure. You are built from it. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was forged long before Earth existed. Stars lived and died so that complex chemistry could emerge. Galaxies assembled so that planets could form. Time passed so that life could notice itself. And even now, those same forces continue their work. Your body obeys gravity. Your atoms follow quantum rules. Your thoughts arise from electrical patterns shaped by biology, but governed by physics. Nothing about you is outside the universe's story, and nothing about the universe is rushed. Stars take millions of years to form. Galaxies take billions. Cosmic structures evolve slowly, patiently. Even dramatic events, supernovae, collisions, collapses, are brief only in comparison to vast stretches of calm. The universe favors endurance over speed. This patience extends to its future as well. As expansion continues, matter thins, stars burn out, light fades, but change never fully stops. Even in a darkened universe, particles decay, black holes evaporate, quantum fluctuations persist. Existence becomes quieter, but not absent. As you drift closer to sleep, consider this gently. You are a temporary arrangement of ancient matter, experiencing the universe during one brief, luminous chapter. The universe does not rush you. It does not demand understanding. It simply allows you to exist within it. And as we move toward the final stretch of this journey, we'll look ahead, toward the distant future, toward how the universe may end, or whether it ever truly does. The future of the universe is not waiting for us. It has already started. Every second, space expands. Galaxies drift farther apart. Light stretches thinner. Nothing dramatic announces this change. No signal, no sound. It happens quietly, everywhere, at once. If the current trend continues, the universe will become colder and darker over immense spans of time. Stars will slowly exhaust their fuel. New stars will form less frequently as gas becomes scarce. Galaxies will fade into collections of long-lived dim stars. Red dwarfs will dominate, burning gently for trillions of years. Eventually, even they will begin to fade. Planets will cool, orbits will shift. Some worlds will drift free as gravity weakens with distance. The night sky, once filled with light, will grow empty. This scenario is often called heat death, not because the universe becomes hot, but because usable energy runs out. Everything reaches equilibrium. No gradients remain to drive change. And yet, even this is not true stillness. Particles decay. Protons may eventually break apart. Black holes slowly evaporate, releasing faint whispers of radiation over timescales so long they defy imagination. Even darkness changes. As you rest now, it may seem unsettling to think of such a distant future, but there is something deeply peaceful in it as well. The universe is not racing toward destruction. It is relaxing, unwinding slowly from a state of high energy into calm simplicity. Some theories suggest alternatives, a universe that tears itself apart, a universe that collapses and begins again, a universe that transitions into something entirely unfamiliar. We do not yet know which path is correct, but all possibilities share one thing in common. They unfold slowly. The universe favors patience. It gives stars time to shine, planets time to cool, life time to emerge, observe, and wonder. And in this moment, this brief overlap between ancient past and distant future, you exist. Not at the beginning, not at the end, but somewhere in the middle, where complexity briefly blooms. As your thoughts drift and breathing slows, remember this: you are not watching the universe from the outside. You are part of its process, a temporary arrangement of matter, aware of itself, resting under an expanding sky. And as the universe continues its slow journey forward, it does so without urgency, without expectation, carrying everything gently along with it. From here, only one quiet question remains: whether endings are ever truly final or just transitions into something we have not yet learned to imagine.
When we talk about the end of the universe, we imagine a final moment, a last page, a silence that follows everything. But the universe has never shown much interest in finality. Every ending we know has been a transformation. Stars end as supernovae and seed new worlds. Galaxies collide and give birth to new structures. Even black holes, once thought eternal, slowly fade. So when we look far into the future, the question is not when does it end, but what does it become? Some theories suggest the universe will continue expanding forever, growing colder and emptier. Others imagine a future where dark energy changes, slowing expansion until gravity takes over again. In those models, the universe could collapse inward, compressing matter and energy until conditions resemble the earliest moments of creation. Not a rewind, not a repetition, but a transition, a universe that breathes, expand, cool, contract, transform. Whether this happens once or many times is still unknown, but the mathematics allows for it, and history has taught us that nature often chooses the path that seems least intuitive. As you rest now, this idea carries a gentle comfort that nothing is truly wasted, that existence does not vanish, it rearranges. Even information may not be lost. Some physicists believe that everything that ever happened is encoded somewhere in the universe's structure, however faintly, in correlations, in radiation, in the geometry of space itself. If that is true, then the universe remembers, not in stories, not in meaning, but in patterns. And those patterns persist even as forms change. From this perspective, time is not a straight line leading to erasure. It is a slow unfolding of states, each giving way to the next. Life appears briefly, consciousness flickers, awareness notices itself, and then moves on. But the universe continues. As you drift closer to sleep, it's worth letting go of the need for conclusions. The universe does not rush toward answers. It explores possibilities. And perhaps that is enough. One final quiet thought remains, not about the universe at large, but about your place within it. How small you are, how temporary, and yet how perfectly connected to everything that has ever existed. From here, we'll gently return to the present moment, to the space around you, to the body at rest, to the quiet awareness that is listening now.
After traveling so far outward, it's natural to drift back inward, not away from the universe, but deeper into it. Because the universe is not something you visited, it's something you're already inside. Right now, as your body rests, gravity holds you gently against the earth. The same force that shapes galaxies, that binds stars, that curves space itself. Your breathing follows rhythms older than language. In and out, expansion and release. The universe works the same way. Energy flows, structures form, systems settle, then slowly change. Nothing is separate. The atoms in your body were forged in stars that lived and died long before the sun existed. They traveled through space as dust. They became part of planets. They became part of you. And now, for a brief moment, they are aware. Awareness is rare in the universe, not because it is fragile, but because it requires patience. Time had to pass, stars had to burn, chemistry had to become complex. The universe took billions of years to create a moment where it could observe itself, through your eyes, through your thoughts, through this quiet listening. There is no pressure in that realization, no responsibility, just connection. As the universe expands, it does not hurry you. As time flows unevenly across space, it does not demand your attention. You are allowed to rest. The cosmos does not measure productivity. It does not keep score. It does not require understanding. It simply unfolds. And tonight, you are part of that unfolding, not as an observer standing apart, but as matter arranged into stillness. Somewhere far away, stars are forming. Elsewhere, galaxies are drifting beyond visibility. In distant regions, time moves slightly slower or faster than it does here. But none of that requires your effort. Everything continues without intervention. As your thoughts soften and edges blur, it's okay to let the universe carry the weight of itself. You don't need to hold it together. You never did. The same laws that guided light across billions of years are guiding this moment toward rest. And as this journey nears its end, there is no closing statement, only a gentle settling, because the universe does not end conversations, it lets them fade into quiet.
At some point, curiosity softens. Questions loosen their grip. Thoughts slow down and begin to drift. This is not the universe ending. This is the universe continuing, without needing your attention. Right now, stars are still burning. Galaxies are still moving. Space is still expanding, gently, patiently. Nothing pauses when you close your eyes, and nothing is lost. Your body knows how to rest. It has practiced this for years. Breath finds its rhythm without instruction. Muscles release what they no longer need to hold. The universe works the same way. After motion comes balance. After brightness comes quiet. After complexity comes simplicity. Not as a failure, but as a return. You do not need to solve the universe tonight. You do not need to remember every idea or image. Understanding is not required for belonging. You already belong. You are made of the same matter that bends light around galaxies, the same particles that drift through interstellar space, the same forces that shaped stars long before Earth existed. And now those forces allow you to rest. As sleep approaches, the universe does not pull away. It remains exactly where it has always been, around you, within you, moving through you. Time will continue to flow unevenly across the cosmos. Light will continue its long journeys. Dark matter will pass silently through everything. None of it asks for effort. So it's okay to let go. Let thoughts dissolve before they finish forming. Let images blur into darkness. Let awareness narrow into something simple and quiet. The universe has carried far heavier things than this moment. It can carry your rest. And if dreams come, they are just another pattern, electrical signals drifting through a universe-shaped mind. If sleep comes instead, that is equally natural, a small echo of the universe's preference for balance. Nothing important is happening that requires you to stay awake. Everything essential is already in motion. So allow the night to take over gently. Allow the vastness to fade into background silence. Allow yourself to become still. The universe will continue expanding. Stars will continue shining. Time will continue its slow, uneven flow. And you, for this brief, quiet moment, are allowed to sleep within it.